The vast majority of people who lose a limb continue to feel its presence, sometimes even feeling pain in a hand or foot that no longer physically exists. This phantom limb phenomenon initially puzzled physicians for centuries, until modern neuroscience revealed a startling explanation. The brain's own sensory map physically reorganizes itself after amputation, and a remarkably simple mirror-based therapy can help resolve the resulting pain. Research consistently finds that the large majority of individuals who undergo limb amputation, estimates typically ranging from 60 to 80%, continue to experience phantom sensations, a persistent subjective feeling that the missing limb is still present, sometimes including detailed sensations of specific finger positions or movements. And a substantial proportion of these individuals, commonly estimated between 50 and 80% of those with phantom sensations, experience genuine phantom limb pain, ranging from occasional mild discomfort to severe, chronic pain that significantly impairs quality of life. V.S. Ramachandran's influential research demonstrated that following arm amputation, the region of somatosensory cortex that previously represented sensory input from the missing hand does not simply go silent. It becomes activated by touch applied to the face, since face representation lies directly adjacent to hand representation in the brain's somatosensory cortical map. In some documented cases, touching a specific point on the amputee's face reliably produced the vivid sensation of being touched on a specific, corresponding finger of the phantom hand, providing direct evidence of large-scale cortical reorganization. This dramatic cortical remapping reflects the brain's fundamental neuroplasticity, the capacity of neural tissue to functionally reorganize based on the pattern of input it actually receives, rather than remaining permanently fixed to its original developmental assignment. Once sensory input from the amputated limb ceases entirely, the now-deprived cortical territory becomes gradually colonized by expanding, actively used neighboring cortical representations, including the face, demonstrating that even the brain's fundamental sensory maps remain adaptable and are continuously shaped by actual patterns of sensory experience throughout life. Ramachandran's mirror box therapy places a mirror vertically between a patient's intact limb and the space where the amputated limb would be, positioned so that the reflection of the intact limb appears to occupy the missing limb's location, creating a compelling visual illusion of having two limbs when the patient moves the intact limb and observes its mirrored reflection. This visual illusion is theorized to help resolve conflicts between the visual system, which shows the limb moving normally, and the somatosensory system, which may otherwise perceive the phantom limb as painfully frozen or contorted. Multiple randomized controlled trials and systematic reviews have found that mirror box therapy produces statistically significant and, for many patients, clinically meaningful reductions in phantom limb pain intensity, particularly for patients whose phantom pain is associated with a subjective sense that the phantom limb is frozen in an uncomfortable or contorted position. Though response varies considerably across individuals, and the specific neural mechanism underlying therapeutic benefit remains an active area of ongoing research and some scientific debate regarding its precise pathway of action. The core principles underlying mirror box therapy, using visual feedback to resolve conflicts between sensory systems and to encourage adaptive cortical reorganization, have been extended beyond phantom limb pain to treat complex regional pain syndrome, a severe chronic pain condition sometimes affecting an intact limb, and to support motor rehabilitation following stroke, where patients practice moving an unaffected limb while watching its mirrored reflection to help stimulate motor recovery in a weakened or paralyzed limb through similar visual motor feedback mechanisms. The phantom limb phenomenon reveals that our sense of our own body is actively constructed and continuously maintained by the brain's sensory maps, rather than being a simple, passive reflection of our current physical anatomy. When those maps are disrupted by amputation, the resulting cortical reorganization can be understood and in many cases therapeutically addressed through the very same neuroplasticity that created the problem in the first place.